Hello, and welcome to my second video on how we discovered how far away the sun is. So in the first one, we saw how far the ancient Greeks got, which was to get a pretty good estimate of how far away the moon is, but a completely hopeless estimate about how far away the sun is. In this video, I'm going to look at what's sometimes called the scientific revolution in the early modern period, which completely changed our view of the universe, and after which it was possible to measure the distance to the sun. So there we are, that's the title. And in this video, we talk about these people. I'm sure you've heard of most of them. And we start with the Copernicus. All of these guys were real polymaths. They did a bit of everything. So he was Polish, astronomer, physician, translator, and economist. He invented the subject of economics, really. But he also came back to the heliocentric model that we saw before Aristarchus had proposed, but it was rejected at the time for very good scientific reasons. Uh, but Copernicus wasn't having any of that. Um, and he did this as the best way to explain what's called retrograde motion. Now, let's see what that means. So, if you look at the path of, say, Saturn in the sky, it does this sort of thing. It wiggles around. It disappears for a while, of course, when it's behind the sun, but it wiggles around like this. And it's called retrograde motion when it goes backwards. Now, people at the time believed basically Aristotelian physics, which suggested that planets had to move in circles. Well, it's obviously not moving in circles, but they had this idea of circles within circles. So the planet was sort of moving in a circle, which itself was moving around another circle. That was the sort of idea, but they could never get that to work. And Copernicus came up with a much better idea. And here it is. So if we look at Saturn in the heliocentric model, so Saturn's quite a long way away. And if you see what happens, as the Earth goes around the Sun quite relatively fast and the Saturn moves slowly, then the view of Saturn from the Earth goes backwards quite often. There it is going. We go back to the beginning, so it's going backwards there and backwards there and backwards. It often goes backwards, and that's a natural consequence of the heliocentric view of the world. Copernicus actually focused on Mars quite a bit, which is more interesting in a way because it doesn't go backwards very often. Let's have a look at Mars. So it goes backwards here, and then it really doesn't go backwards. For a long time, it goes forwards all the way around, blah, 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 blah. Da, 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 and then whoop, goes backwards a bit, and then off it goes again. So that's a really more convincing argument in a way that heliocentric model explains this really very, very well. So that's his one contribution. Of course, you don't have to accept that, and many people didn't, as we shall see. But the other thing he did was to calculate the periods of the planet's orbits. That's the period relative to the stars and the sun. So it's easy enough to see where the planet comes back to the same point against the stars from the Earth. But by then the Earth's moved, and so it's not really in the same place at all. To work out where it's actually back in the same place, as it were, viewed from the sun, is much harder. It's not impossible, and once you've got hold of the heliocentric view, you can get a pretty good idea just by looking at those points in time where it goes backwards. But you can refine that very considerably by using old data. And Copernicus used data going all the way back to the Babylonians to get a really very accurate version of what the so-called sidereal periods, that's the periods against the stars and the sun. That's an important contribution. So the next famous guy is who's seriously involved is Tycho Brahe. So he was Danish. He was a truly obsessive astronomer. It was all naked eye stuff at this point. We didn't have telescopes. Um, just an illustration of how obsessive he was. The King of Denmark gave him an island to build an observatory on, and he did that. And he built these enormous instruments to do naked eye astronomy, so he could look at the stars with great accuracy. But he got fed up because the wind affected these enormous instruments, and so he dug a big hole and built himself a new observatory at the bottom of the hole, so his enormous instruments wouldn't be affected by the wind. Anyway, he reckoned he could observe things to 1 arc minute of accuracy. That's a 60th of a degree, which is corresponds to roughly a sixth of a millimeter at arm's length. So you imagine what a sixth of a millimeter is at arm's length. That's a very small angle. I didn't hold with this heliocentric nonsense. He sort of accepted that it was an easier way to do calculations. So he sort of accepted that it was right in that sense, but he didn't believe that was what was really happening. And let me show you what he believed instead. So what he said was, well, okay, I'll accept the idea that the planets are going around the sun, but I'm not having the Earth going around the sun. I think the sun must be going around the Earth. So let's look at the consequence of that. Here in this picture, we have Copernicus's view of the universe. I've just got Mars, the Earth, and sorry, Venus, Earth, and Mars on this picture, and you see they're going round in sort of an orderly fashion. Now, what's happening here is that the sun's going around the Earth, but Venus and Mars are going around the sun, and actually, it's completely equivalent in terms of what you see when you look out to the sky. So, for example, at this point in the cycle, looking towards Venus from the Earth, you're going in that way, as you are here. That's parallel. And looking towards Mars is that way, which is that way. So in terms of looking out from the Earth and seeing the night sky, these views are completely equivalent. But what attracted Tycho Brahe to this view for calculation purposes was, let's look at the orbits. So there's Mars's orbit. It's pretty crazy because it's going round the sun, which is in turn going around the sun. It's going around the Earth, and actually Venus is even worse. So he accepted this for calculation, but for sort of philosophical reasons, he believed this must be what was really going on. And we can't separate these views just by looking at sky. We need something else, and it turns out what we need is Newtonian physics, because this one doesn't work in Newtonian physics. But we'll get there. Okay, so let's just see what people thought physics was about at the time. They still believe what Aristotle taught them, which is that objects remain at rest until acted upon by a force. Well, yeah, that's not what Newton says, and it's not right, but it's a sort of plausible thing to believe. And that forces are of two sorts. There are violent forces and natural forces. So violent forces are exerted by one body on another. So, for example, if I throw a ball, I'm exerting a violent force on the ball. And then there are natural forces which are determined by the nature or sometimes soul of an object. And for example, things like rocks have a nature, or if you like, a soul that causes them to fall. Plants have, in addition, I mean, plant will still fall to the ground if you drop it, but plants have a vegetative soul which controls growth and reproduction. So this sort of slow motion is caused by the vegetative soul of the plant. Animals have also a sensitive soul that causes them to run around. And people actually have a rational soul in addition to that, which causes them to do rational things. Planets also have a soul, or at least a nature, which is perfect because, they're heavenly, so they're perfect. And that means they move in perfect figures, which are circles. So planets have to move in circles. Well, goodness knows why anybody would leave that for 1,000 years, but they did. And so Brahe still believed this, really. And actually, so did Kepler. We'll come on to that. So the next guy is Napier, who isn't really an astronomer, but he is a mathematician. Like Brahe, he's rather obsessive. But what he's obsessed about is finding better ways of improving calculation, particularly for astronomers. We'll be seeing an enormous amount of calculation that's done in the course of this period, prodigious numbers of calculations. And really, they wouldn't have been possible without Napier because he invented logarithms, which made those calculations much simpler. Of course, they were improved by John Wallis a little while later, who had the bright idea of making them what we would say is base 10. Anyway, okay. Now, next guy, Galileo Galilei. He's very famous. He was the first person to use a telescope to look at the heavens. He didn't invent the telescope, as you will sometimes hear. That was invented for terrestrial use, but he turned it to the skies. And what did he find? All sorts of things which revolutionized astronomy. He made many discoveries. So one of the most important is the phases of Venus. Now let's look at that. So Venus, if you look at it with a telescope, you can see that it has phases a bit like a moon. There they are, as it goes around the sun. Now that really kills off any notion that the Venus goes around the Earth. It's got to be going around the sun for that to make any sense. So that really nails down that part of the Copernican theory, which says that Venus goes around the sun. There's now no arguing with that. Um, so that was the phase. The other thing he did was to discover the moons of Jupiter, and it showed that they could be used to synchronize clocks as they go regularly, and you can see them from anywhere on the world. So you could synchronize clocks with them. That'll play an important part in the story later. He also made a step towards killing off Aristotelian physics and advancing towards Newtonian physics by what we might call Galilean relativity. So what he said was this: if you're on board a ship on a calm sea and you're in a cabin with no windows, you can't tell whether the ship's moving or not. That's a revolutionary idea. It's quite different from what from anything that you deduce from Aristotelian physics. And of course, it's completely consistent with Newtonian physics. And it is a sort of first step. And I'm sure Newton would have read this, and it would have been part of the formed part of the formation of his theories. Now, Kepler. Kepler is really the heart of this story, I think. And if anyone in this whole story deserves to be called a genius, apart from Newton, of course, it's Kepler. So he was a polymath. He was a student of Brahe, and he actually stole part of his data. They got cross with each other for some reason. So he wrote the first science fiction novel in Latin, of course, because everything was in Latin in those days. Um, this was the time of witchcraft, so he successfully defended his mother against an accusation of witchcraft, probably motivated for political reasons rather than because anybody thought she actually was a witch. Anyway, and he established his laws of planetary motion, despite still believing Aristotelian physics. So that's quite remarkable, actually. But he also incorporated magnetism, which had just been discovered. So he believed that had a role in moving the planets around their orbits. So what were his theory? So the one that everybody remembers is it tells you that the orbit of a planet is an ellipse with the sun at one of the two foci. I'll come on in a minute to see exactly what that means. The others perhaps are less important to focus on, but one is that it says that a line segment joining the planet to the sun sweeps out an area as it moves, and the areas it sweeps out equal areas at equal times, which means that when it's further from the sun, it moves more slowly, and when it's closer to the sun, it moves faster. And then this one, which relates um, different planets' orbital periods. So you didn't need to focus too much, but it says the square of the planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit. In other words, it's the size of the orbit. So that enables you to compare the orbital periods of different planets. Or if you know the orbital periods, it enables you to calculate the size of the orbits, the relative size of the orbits. Right. Now then, we know that he did that, but how did he do it? And this is the most extraordinary thing. So let me show you. Right, so we want to calculate the orbit of Earth and of Mars. We don't know either. I mean, on the face of it, that's impossible, isn't it? Because you're looking at Mars from the Earth. And so as you watch Mars move, and the Earth's moving too, and you don't know how it's moving. So you don't, I'm sorry, it's just impossible, really. Well, but it isn't quite impossible. So what do? You start with the point where they're in opposition, and what that means is that the Sun, the Earth, and and Mars are in a straight line. So you can work out when those points in time are, and you can put Mars on a piece of paper and the Sun on a piece of paper. You don't know where the Earth is; it's somewhere on that line, but you don't know where. Okay. Now the clever thing is, you now move on one Martian year. So Copernicus has told you how long a Martian year is. So you move on, and so Mars is in the same place on this picture, and so is the Sun, and so are the stars. But now we can work out where the Earth is because Brahe's observation tell you what this line is. The date and time tell you what this line is. So you can plot Earth on this piece of paper. And then you can do it again another Martian year later, and another, and another, and another. So you end up with 5 points. I think it was five you did. where you now know 5 points on the orbit of the Earth. Right, well, that's a start. But now this is the genius bit. What you do now is move on a couple of days or something like that, I don't know, a little while, and guess where Mars is. You don't know where it is. It's going to be somewhere near where it was 2 days ago, but you don't know quite where. But now you can play the same trick and um, plot the Earth from that point of Mars and several years apart. So, that's another year, another year, and another year. Oh, and this one's over here. What? So, what that tells you is that this guess of where Mars is hopelessly wrong because we know this light pink Mars has got to be quite close to the red Mars, but all these light green Earths have got to be pretty close to the dark green Earths. And if you move this around, you can sort of get to a point where that's more or less true, and then you can lock it in place where it's true. And so that gives you more points on the Earth's orbit and another point on Mars's orbit. That's pretty clever stuff. And just think about how many calculations are involved there. And then you do it again and again, and that way, and do it over and over again, and you get Earth's orbit and you get some of Mars's orbit. Oh, that's pretty good. Whoops. Right. Well, actually, then it's not so bad because now, once you've got Earth's orbit, you can just take any 2 Martian points a Martian year apart, and you can plot Mars. So that gives you Mars's orbit. There it is. Now, you can just imagine how much calculation there is involved in doing it. Of course, he didn't have GeoGebra to do it all for him. He had to do it all with pencil and paper and log tables. And over again, he's doing trial and error to find where Mars fits on this piece of paper. And no doubt, when you've done a few, you realize the second one you did wasn't quite right, so you need to go back and do it again. And there's a simplification I've made here. This picture makes it look as though the Mars orbit and Earth's orbit are in the same plane. They're not quite, they're tilted. So you have to allow for that as well. But he ended up showing that Mars's orbit and Earth's orbit are elliptical. That's pretty amazing. But more amazing still, let me show you this. Now then, look at the difference between a circular orbit and an elliptical orbit. So in black here, we have a circular orbit around the sun. That's at the center of the circle. And here we have a succession of ellipses. And these ellipses, there's a thing called eccentricity, which is a number which tells you how uncircular an ellipse is. And that's a sort of range of values. And these are ellipses with one focus at the sun, and the other focus is over here somewhere. So they're symmetrically placed in the ellipse. Now then, what you notice is that when the eccentricity is very small, you can't really tell this ellipse isn't circular. It's moved, it's eccentric, but it really hardly looks different from a circle. In fact, if I put a circle in, here we are, there's that red one. So there we are. That red is a circle which is shifted by the same amount as the ellipses. And it's very similar when the eccentricity is small. But Kepler told them apart. Now let's just see how eccentric the Earth's orbit is. Not very. In fact, you can hardly see the red thing at all. And yet Kepler was able to tell that the blue one was right and the red one was wrong. Just shows how extraordinarily accurate. Even for Mars, Mars is slightly more eccentric, and at least on this picture you can see the red circle. But again, Kepler was able to see that the red circle didn't work. The blue ellipse did work. It's really only when we get to Mercury that the eccentricity is big enough that you can really tell the difference on this sort of naked eye illustration. So that's pretty remarkable. We've now got elliptical orbits, and we've got all these other rules about. So we not only we know what the orbit is, but we know how the planets move around them. That business about sweeping out equal areas in equal time enables you to calculate exactly where any planet would be at any one point in time, moving around its elliptical orbit. And that's a very important point. So you can make predictions of where the planets are going to be, and very accurate ones. Okay. It's fair to say, though, that you wouldn't, it would be a rational position not to believe Kepler because the difference between those red and blue figures is so slight that you could defend, it would be a defensible position to say, well, I just don't believe it. The data is not accurate enough to tell those. Um, so what really nailed it was Isaac Newton. He was a farmer, and that's not what you remember him for, and a workaholic, polymath, and not a very nice person, I think. Anyway, but he was definitely a genius. According to Lagrange, the greatest genius that ever lived. And Lagrange was a Frenchman, so for him to say that about an Englishman, pretty remarkable. And anyway, I don't suppose many people would disagree with that. And he published his most famous book, The Principia, in 1687, in which he, well, amongst other things, unified celestial and terrestrial physics. So up until this point, astronomy was really the only exact science, and anything that you did on Earth was pretty wishy-washy, really. And they had all this Aristotelian nonsense trying to behave it, explain it. But once Newton had showed that planets obey the same rules as apples do, suddenly it became possible to do real science on the surface of the Earth. And he came up with these laws. Again, we don't need the detail really, but I'm sure you know all this stuff. The first one is that a body remains at rest or moves in at a constant speed in a straight line unless there's a force. So that's quite different from the Aristotelian notion that a force is what moves something. A force is what changes the nature of the movement in Newton's rules. And in particular, the net force is F equals ma. The force is equal to the acceleration times the mass, and equal and opposite. If exerts a force on B, B exerts an equal and opposite force on A. And then the gravitational force, which is the force between two bodies like the sun and the planet, it's symmetrical, as the third law says, and it's proportional to both masses and inversely proportional to the distance between them. Now, the significance of that for our story is that Newton's law implies all of Kepler's laws. It says planets will move in elliptical orbits, and they will do that sweeping out of equal areas at equal times, and they will do that cube of the period square of the or whatever it is, the thing that relates the different planets together. All those are implied by Newton's laws, though it's not at all easy to show that. It's quite a difficult piece of mathematics, that. But what that meant is that really you could forget about disagreeing with Kepler because the Newton had shown that Kepler was right, and actually you can forget about disagreeing with Newton too because Newton's laws, Newton's and Kepler's rules support one another so strongly that it's really no longer possible to disagree with either of them. Um, and so that meant you could concentrate on a view of the world that you've now acquired, which could lead to much improved predictions. Because now we had an accurate map of the solar system, so we know the elliptical orbits of all the bodies, we know how they move around those orbits, and we know how they relate to one another in size. The only thing we don't know is what the scale is. So how far the Earth is from the Sun. Once we knew one of the, if we knew any one of those distances, um, we'd know them all. And we know them forever because we've got a predictive model of the solar system. So if we could measure the distance to any planet at any point in time, that would give us the scale. And this moving map that we've got a solar system now has a scale on it. And so we can tell where anything is going to be forever, essentially. So this is the notion of the clockwork universe that you'll sometimes hear about, which is this model of the solar system, which Kepler's laws predict and Newton's laws underpin, which enable us to work out exactly where anything's going to be pretty well forever. So what's actually going to be in the next video is observations of the transits of Venus, which were when Venus goes in front of the Sun, which enables us to measure the distance to Venus. So people have tried using close approaches of either Venus or Mars to a star up in the sky and try to measure the parallax. But yeah, it's not tricky to get any real accuracy out of that. But nevertheless, the astronomical unit, that's the distance to the sun, had been narrowed down to something like sort of 20,000 Earth radii, which isn't bad, but they wanted to get better. And so they did. And this is how. So it starts with Edmund Halley, he of comet play, fame, in 1716 predicted that transits of the Venus in front of the sun would occur on these two dates some 50 years hence. So that gives you a hint about this accurate prediction business that I've been talking about. And he said, if you could time those transits to the nearest second, you could effectively create angular resolution to about a tenth of an arc second. So you could get a tenfold increase in accuracy of our estimates of which would ultimately give a much more accurate version of how far away the sun is. And the international scientific community responded to this challenge, and it responded in spades. And that's going to be the story in the third video in this series. So I'll see you then.